Hope all of you are well. So I welcome all of you to this session. So this is the first video lecture regarding the introduction to the multiple integral. So in this video lecture we are going to discuss about the basics of the multiple integral, just like double integration and triple integration, the definition and the formula, and some solved question for your practice purpose. So let us be connected. So first of all, before we go to the double integration, we need to understand the concept of the line integration or the single integration that already we have learned in our class 12. So first of all, we need to understand the definite integral for one dimensional function, right? So now suppose we are having a function y equals to fx. We consider this function is an integrable function and it is a real valued function. Over the real line we can be able to integrate it. Now the definite integral usually we have seen in this structure, that is integration a to b y into dx. In place of y we can write down fx, so it can be written as integration a to b fx dx. So all of you are habituated with this integration. Now what does this integration a to b fx dx represents? Basically this integration represents the area under the curve y equals to fx, which is bounded by the function y equals to fx along with the boundaries, that is x equals to a and x equals to b. Now let us try to imagine the concept through the diagram. Suppose we are having the x-axis and y-axis here, and we have the function y equals to fx. Now the points x equals to a and x equals to b, these 2 points are situated on the x-axis. So how to do this integration or how to perform this integration? We have to draw some perpendicular from x equals to a to the function and from x equal to b to the function. So this height, basically we can write it as a function of a, that is f of a, this height, and this side, this height you can understand as f of b. Okay, now how to do this integration? We have to divide this whole region x equal to a to b into equal number of sub intervals. How it can be done? Just by taking this thing, that is b minus a divided by n number of equal sub interval we have to break. Now for each sub interval we have to draw some perpendiculars like this. So we will get some small rectangular shape of region that I am shading here. This type of shape we will have. Now all of you know how to calculate the area of a rectangle. That area of the rectangle can be calculated by taking the length into breadth, right? So if fa is the length and delta x is the breadth, so the shaded rectangle just now I have drawn, it is having the area fx f of a into delta x. The next point should not be fa, the height should not be fa, because the height is going to change with respect to the y equals to fx function. So for this case, if we are having n number of points x1 x2 xn, from each point we can find out the small rectangles, and the each and every rectangle area we can calculate by this fx1 into delta x, fx2 into delta x, fxn into delta x. Now whenever we will add all these rectangles together, we will get the value of the integration, that is the area under the curve lying between y equals to fx, x equal to a and x equal to b. So the limiting form, it can be written as limit n tends to infinity summation I equals to 1 to n f of xi into delta x. We will assume that this number of sub intervals will be infinite, so this error should be less, because we are just replacing the area by the rectangles, so there should be some error in the top. So this area can be this error can be less if we increase the number of rectangles or the number of points. So this is the basic definition or limit sum definition of the integration or the definite integration, line integration. Now we come to our concept of the double integration. So how to understand this double integration concept? Suppose we are having, in place of this is quite similar. If you have understood the line integration, then also you will be able to understand it. It is quite similar to the previous one. So here, in place of y equals to fx, we are having a function z equals to f of x comma y, which is a function of two variables, which is a real valued integrable function, which is defined over a bounded region R. We have to remember this, the region R should be a bounded region in the xy plane. So where this R region should lie, the region should lie in the xy plane. For your understanding purpose, here I have drawn the xy plane and a region R, which is enclosed by a closed smooth curve C. Now to do the integration, just like before, here we are having a surface in place of a straight line. So over a straight line we can draw just some breaks, that is the sub interval, but here we cannot make the breaks, we have to do the grid. So here some vertical axis and vertical lines and horizontal lines we have made, so many grid points has been created. So if we just look at a particular grid, so this grid, suppose we have focused here, we are thinking that this grid is having the length as delta x and the breadth is delta y. Now to imagine z equal to f of xy, here I have drawn one surface, that is z equals to f of xy. Okay, so this is the surface z equals to f of xy. Now this surface we have to integrate over the region R, which is situated in the xy plane. So how to perform this? Suppose we are thinking about this particular rectangular box or the grid in the xy plane. So from this grid point, basically the same concept, we have to draw the perpendiculars to the surface z equal to f of xy. So whenever we draw the surface, draw the perpendicular, it will create a surface which will bound one region, solid region. So basically, if throughout the region R we will make so many perpendiculars and try to just take the sum, then it will basically create the volume of a solid body. So what is the difference between a line integral and a double integral? The line integral represents the area under the curve bounded between two lines x equals to a and x equals to b. In place of the case of double integration, that is defined by double integration of f of xy into dx dy or dA, that represents the volume of a solid body. So the similar limit sum integration formula we can write down for the double integration as double integration over R f of xy d of a, this is equals to limit delta a tends to 0, limit summation I equals to 1 to n f of xi yi into delta a. The concept is quite similar to the previous one. Now the geometrical representation, from that we have be able to understand that this double integration basically represents the volume of a solid body which is bounded by z equals to f of xy, z equals to 0, that is xy plane, and the region R which is situated in the xy plane. Now today our task is to understand the first case of this double integration and do some problem based on that. So first we come to the solution methodology, how to solve this kind of integration problem in our exam. So first we will start with the type 1 case, that is the constant limit case. So whenever in the double integration we see both the limits are constant, then how to approach towards that problem? Suppose we are having the double integration over the region R f of xy dx into dy, where R region is prescribed by a less equals to x less equals to b and c less equals to y less equals to d. One most important thing now we are going to explain, so please be careful about that. Now whenever this type of question will be given to us, our first task will be have to understand the region R which is situated in the xy plane. So here we have drawn the x-axis and the y-axis, and we have given the ranges x equals to a, so that will be a line parallel to y-axis, x equal to b, another line parallel to y-axis, y equal to c, a line parallel to x-axis, y equal to d parallel to x-axis. So inside these four lines, one region has been bounded, this shaded region. So this is our region R, over which any function, that is the z equals to f of xy, we have to integrate. Now if this region R is in the form of a rectangular shape, is in the form of a rectangular shape or maybe a square, but all the four, there will be four lines only. Okay, there will be no other kind of shape other than any rectangular shape. If the region is form of the rectangular shape, then the double integration can be performed using the following formula. So what does the formula represents to us? I equals to integration c to d, y equals to integration c to d. Inside we will have to do integration x with respect to a to b, f of xy with respect to dx first. Okay, thereafter we have to perform the integration with respect to dy. So if we are having the double integration dx dy, so with respect to one variable, first of all we have to perform the integration. At that time we have to keep the other variable as fixed. We will not change the other variable, or we will not do the integration with respect to the other variable. Okay, while doing the integration with respect to one variable, rest of the variables and the terms will be considered as the constant term inside the integration. So whenever we will perform x equals to a to b f of xy dx, integration will happen only over x, y or rest of the terms we have to consider as constant. Thereafter we have to substitute the limits of x, and we have to go outside this bracket and perform the rest of the integration with respect to y. Same integration also we can perform in this manner. That is, you can perform the integration with respect to y first, that is y inside and x outside. Now why this thing is allowed? I have given equality in these two integration. Why this thing is allowed? Because the region is a rectangular shape of region. That's why this integration is allowed. That is, with respect to whatever, which variable you want to do, you can perform the integration with respect to that variable, and thereafter you can switch to the other variable. But limit you cannot change. Limit will be as it is. Limit is not getting changed anyhow. Now let us come to solve some problem and try to understand this concept using the problems. Now suppose in your exam one problem is given in this manner, that is 0 to 2, 0 to 1, 4xy dx dy. Now it is not mentioned in this case that which variable is having the limit 0 to 2 and which variable is having the limit 0 to 1. The technical case is there. Conventionally we consider whatever the integration is the coming first from inside, that will be the limit of the inner variable. Okay, so inner side we can see the variable dx is coming. So this 0 to 1, basically it is the limit of variable x, and 0 to 2 is coming outside, so it will be the limit of variable y. So this is the first and foremost thing, you have to understand it very carefully. So we have to write down y equals to 0 to 2, x equal to 0 to 1, 4xy dx dy. So I have arranged in this manner. Y limit is outside, so y integration we will perform later. X integration we have to perform first. Now whenever we will perform with respect to x, we have to think 4 and y both are as the same constant. So 4y is been taken out. X integration with respect to dx is x square upon 2. Limit of x we have to substitute, that is 0 to 1, and the integration, last integration that we have to perform with respect to y. Now that is 0 x square, and the limit is x square by 2, limit is 0 to 1. So after putting the upper limit and the lower limit, we will get 1 by 2 from there, and thereafter this 1 by 2 and 4 get adjusted and 2 is coming outside. Now we have to integrate y with respect to dy, so that is y square divided by 2. Now limit is 0 to 2, so we can get the value of the integration as 4. So this is the way that we have to perform this double integration. It is quite easy to understand and apply also. Now let us come to the another problem. Suppose the integration is given 1 to 2 and 0 to 1 x square plus y square dx dy. Again they have not mentioned anything as the limits, so by conventional way we have to understand the case. So since 0 to 1 is the first integration inside, so this should be the limit of the first variable x, okay, and thereafter 1 to 2 is the limit of the outer variable, that is y. So we have to write down accordingly, that is y is ranges from 1 to 2 and x is ranges from 0 to 1. Now x square integration is x cube by 3. Y square will be treated as a constant, so constant dx integration is x into constant, so x into y square. Limit of x is our 0 to 1, so wherever we have seen x, we have to put x as 1, upper limit, minus 0 as the lower limit. So it will come 1 by 3 plus y square 1 to 2 dy. So 1 by 3, the limit integration of 1 by 3 dy is y upon 3, and y square integration is y cube divided by 3. Limit is 1 to 2, so we have to substitute the upper limit 2 first here, so it will come 2 by 3 minus lower limit minus 1 by 3, plus for the second function 2 cube 8 by 3 minus lower limit 1 by 3. So 1 by 3, 1 by 3 and 2 by 3 will get cancelled out, so the result is coming as 8 upon 3. Now the next concept I have given here as the triple integration, though the concept is quite similar, basically the same thing we have to understand, but here one more variable will be added. In place of x and y, there will be another variable, that is x, y and z, okay, but the concept is similar. Since it is the constant limit case, so we can do it with the double integration also. So here also you can be able to see nothing is mentioned inside this integration, that which one is the limit of which variable, that is 0 to a, 0 to b or 0 to c. They have not mentioned anywhere which one is the limit of which variable. So as per the convention, since dx is coming here first, so we have to think that the variable x is having the limit 0 to c, the variable y is having the limit 0 to b, and the variable z is having the limit 0 to a. So first we have to perform this function integration with respect to x. So x integration, x square by 2, y and z are since constant, so it will be treated as constant only, so x into y, x into z, limit is 0 to c. dy dz will be keep as it is outside. Now limit we have to put of x, so after putting the limit, what we are getting side by side, you can be able to understand, that is 0 to a, z equals to 0 to a is there. Now y limit is also 0 to b, and we are having c square upon 2 cy plus cz, that we can see from here. Now we have to perform the integration with respect to y. So c square by 2 is constant, so dy only will be there, so it will come c square by 2 y only. Thereafter y integration is y square divided by 2, and cz both is constant with respect to y, so it will come cyz. Limit is 0 to b. Now we have to substitute the y value or y limit. So after putting the y limit, we get the value c square b upon 2 plus cb square upon 2 and cbz. So only one variable is remaining, that is z. So with respect to z, we have to integrate and substitute the value 0 to a, upper limit and lower limit. So ultimately the answer is coming as a plus b plus c into abc divided by 2. Okay, now we come to the next problem, that is problem number 4. So we have to evaluate integration 0 to pi integration 0 to a r square dr d theta. So here the integration is given in the polar coordinate system. Though it is in the polar coordinate, but the limits are being given as the constant limit, so we can apply the case that we have just now understood. So here nothing is mentioned as per the problem, so what we can consider, that is dr, that is r is having the limit 0 to a and theta is having the limit 0 to pi. So r square we have to integrate first with respect to dr, so it will come r cube divided by 3 and limit is 0 to a, so it will come a cube upon 3 here. A cube upon 3 is constant, so you can take it outside, so it will come as 0 to pi d theta, and d theta integration is theta only, upper limit pi, lower limit 0, so pi minus 0 it will come pi only, so it is coming pi a cube by 3. In the next video lecture we are going to learn the second type and little bit critical type of the double integration, that is the double integration for the variable limit case. Thank you all.